Hello, welcome back to Math 332, Linear Algebra. Today we are going to talk about a very important concept in mathematics, in engineering, and science, which is the concept of eigenvalues and eigenvectors. Actually, we use that in engineering and physics too. So think of it, this is like a three-part series where we're going to spend the first video talking about computational of these eigenvalues and eigenvectors, introduce some terminology and notations, and then we are going to look at how we are going to use this concept of eigenvalues and eigenvectors, and we use it to diagonalize a matrix. So we have to talk about what diagonalization means, and then when can we actually, under what circumstances, we will have enough eigenvectors to make the diagonalization work. Sometimes we can make it work. So under what circumstances it won't work. And then finally, we are going to look at one or two applications in diagonalizations. There are many applications for diagonalizations. You probably heard of Markov chains and this and that. But we are going to look at two examples. One is how to use diagonalizations to solve system of differential equations, and how to use it to solve difference equations. So, all right, so let's look at the first video right here, and we are going to look at some basic concept. So we always look at the square matrices, so in this case 2 by 2. So when we talk about eigenvalue and eigenvectors, all the matrices involved will be square matrices of size n by n. So you have this matrix A, and they have two different vectors. So if you multiply AU, so think of it, this is a vector U, and you multiply A with U, you actually get negative 4U in this case. So it's like U is this vectors, AU is opposites, it's negative 4U. So this is actually kind of special because when you multiply a matrix with a vectors, you linear transform that vectors, right? So it would not always end up to be like parallels to the original vector. So this is like a very special case. And you can see it won't always happen this way, because if you take a vector v's and you multiply them, this vector v, you would not be able to write as a scalar multiply the v itself back. So this is like AU is a scalar multiply u, but in general that would not happen. So this is an example to show that that would not happen. So this is a very special situation. And when that happened, okay, we will call this scalar as an eigenvalue for this matrix A, and the vector x, like in this case AU equals to negative 4U, this is going to be known as the eigenvalue. This is the meaning of eigenvalue. So this is called the eigenvalue of the matrix A, and the vectors that make this works is going to call the eigenvectors. So the definitions of eigenvectors and eigenvalue is very straightforward. It says that if you have n by n matrix, lambda is called the eigenvalue of A if you have AX equal to lambda x, where x has to be a non-zero vectors. Lambda can be zero. Lambda can be zero, but the vector which we call eigenvectors can never be zero. So if you can find a non-zero vector such that AX equal to lambda x, lambda is going to be known as the eigenvalue for the matrix A, and the vector x is going to call, it's going to be said to be the eigenvectors of that matrix A corresponds to that eigenvalue lambda. So that's the definition and terminology. So the question now is, how do we find, so given this matrix A, how do we find that vectors which is special and such that A of U is equal to minus 4U, where you have this constant, this so-called eigenvalue, and how do you find the eigenvalue? So this is what we are going to do next. So the theorem says that if you have a square matrix and you want to find the eigenvalue, then you find it by computing the determinants of A minus lambda I and set it equal to 0. And this is known as the characteristic equations of the matrix A. This is actually pretty straightforward. It's not a big mystery that why we can get eigenvalue from doing this computation. So let's look at the definitions carefully again. So if you can find a vector x, non-zero vector x, key, it's a non-zero vector x, has to be non-zero. That's the definitions of eigenvectors. Eigenvectors cannot be zero. Eigenvalue can be zero, but eigenvector cannot be zero. So if you want to find a non-zero vector x such that ax equals to lambda x, then it is the same as if you are trying to solve the system ax, right, minus lambda x, okay, equal to 0 vectors. And so you can factor out the x. So this, when you factor out the x, this is how you properly factor out the x. Okay, so now you are kind of like try to solve the system of homogeneous equations. So basically kind of like try to solve bx equals to 0, right? So we know, again, this matrix is still square matrix, n by n. So it's kind of like solving an n by n system, bx equal to 0. And you're looking for a non-zero vector. So you want this to be non-zero. So you want it to be non-zero, you better make sure this matrix B is not invertible. Because if this matrix B is invertible, so if this matrix B is invertible, you will have to, you can invert it, and you will have x equals to b inverse times 0, which will give you 0. And this is not what we want, because we want x to be non-zero. So in order to make sure b not invertible, okay, so in order to make sure b not invertible, we will have to make sure that determinant of b is 0, because determinant of b equal to 0 will make b not invertible. All right, we want it to be not invertible. We don't want it to be invertible. Invertible will give x equal to 0. We want x to be non-zero, so we better make sure b is not invertible. And from theorem, we know that a matrix is not invertible if and only if the determinant is 0. So now this is our matrix B, right? So in order to make sure that a minus lambda I times x equal to 0 has non-trivial solutions, to have non-zero solutions, you better make sure that a minus lambda I is not invertible. That will make determinant of a minus lambda I 0. So that is the reason you have this theorem. And so now it gives us a method to compute the eigenvalue. So for example, if you take this matrix A, and you want to find the eigenvalue, so we take a minus lambda I. So make sure you know what this thing means. Lambda I in this case is going to be 1652 minus lambda 0, 0 lambda. That is lambda I, right? So if you do that computations, you will get 1 minus lambda. This is going to be 6, and then it's going to be 5, and then you have 2 minus lambda, and you set it equal to 0, compute a determinant. You found 2 lambda equal to -4, and lambda equal to 7. These are known as the eigenvalue. And what you do now, once you have this, so the first step of the eigenvalue and eigenvalue problem is to find the eigenvalue. So once you have the eigenvalue, so in this case, lambda equals to -4. Now, how do you find the x then? So remember, we want to find ax equals to lambda x. So apparently, one of the lambda is going to be -4, as we already know from the example before. So this is -4x. The question is that how do we find the x now? So it's basically the same as if you are saying that you are trying to solve this system of equations. Okay, which means that you want to solve the system of equation now. So solving this system of equations, a is known, lambda is known. So in this case, if you put lambda equals to -4, so put lambda equal to -4, you will have 5, 6, 5, 6, and you want to solve this. So you want to find the x. And we will get the augmented matrix that looks like this, which will row reduce to this. And this is perfectly normal because we want non-zero solutions, so we want it to be non-invertible. So you must have a row of 0. So everything makes sense. So here, this is your x and y, and try to solve for the x and y. So again, this is what we learned a long time ago. So x is -6 over 5y, and y is y, the free variable. So you get xy equal to -5 over y, factor out the y, you have that. And so you see that eigenvectors, you have a whole bunch of eigenvectors, and apparently the eigenvectors are all in this form. So from the terminology that we know before, this basically means that all the eigenvectors is a linear multiple of these vectors, and we just want one eigenvector. So we just want one particular eigenvector, so you can pick something that is nice. So nobody likes fractions, right? Fraction is such a loser. So you can take y equals to let's say 5 or -5. So let's take y is equal to -5. So you have 6 here and -5 here. So let's just choose this as our eigenvectors. So let's just take this as our eigenvectors. So this will be an eigenvectors corresponds to eigenvalue lambda equals to -4. So for lambda equal to -4, this will do the job. And this is actually the u that we found in the very beginning. So this is actually the u that we found from the very beginning. So we have that. And we actually also know that lambda equal to 7 is also another eigenvalue, which means that we should be able to find another x so that this is true. So the same thing here applies to lambda equals to 7. Substitute that thing in. So you have that. So you solve the system of equations. you get that all the eigenvectors corresponds to this eigenvalue. So every eigenvalue have an eigenvector. So you have to make that clear by saying that the eigenvectors corresponds to this eigenvalue. It's going to be a multiple of 1, 1. So let's just pick x equals to 1, 1 instead. So you can also check your computation. A11 actually will give you 711. And again, by definitions, this is going to be your eigenvalue, and this is going to be your eigenvectors. So remember, computationally, it's pretty easy to find the eigenvalue and eigenvectors. First, you find the eigenvalue through the determinant, and then you substitute the lambda back to the linear equation and solve for the x. And that's it. So this is pretty straightforward in terms of computation. Obviously, this is not going to be very easy if you have matrices that's big, like 3 by 3, 4 by 4. The first problem that you will encounter for big matrices is the determinant is not easy to compute, and you will have a polynomial of degree 3 if you have 3 by 3 matrix, that polynomial degree 4, polynomial degree 5 for matrices of size 4 by 4 and 5 by 5. So solving it, finding roots for this polynomial is a hard problem. If you have studied algebra in high school, you know that's a polynomial degree 5. How do you find roots? That's generally not easy, and sometimes you don't have nice solutions and things is a mess. But right here, we are not going to tackle all this computational numerical difficulties. We are just going to get you the concept, so everything works well, numbers are nice. Okay, so don't worry too much about that. So and in particular, we're using a 2 by 2 example right here, so everything works very well. I just don't want you to get the impression that everything is going to be easy. Well, life is hard, and real life problem is hard. So this is a toy example. So make sure you know how to do the toy example. Otherwise, don't think you will survive. Okay, all right. So this is a new definitions right here, because from the computations, we see that when you find the eigenvalue, eigenvectors, the eigenvectors is actually spanned by some vectors. Your eigenvectors is also spanned by some vectors. So you can see the eigenvectors correspond to lambda equal to 7 is spanned by 1, 1. The eigenvectors corresponds to lambda equal to -4 is spanned by all these vectors. So we are going to define, we're going to kind of like find a proper language to put all this thing in perspective. So we're going to give you these definitions, which says that if you have a matrix A, size n by n, you have a lambda, which is the eigenvalue of A. Then the collection of eigenvectors corresponds to that lambda is together with the 0 vectors is called an eigenspace of the lambda. And this is the notation. Eigenspace is going to be all the eigenvectors, put a 0 first here, and then put all the eigenvectors, corresponds to this lambda. So it is a set, consists of all possible eigenvectors and together with the vector 0. So this is a vector space known as the eigenspace. And so, for example, the eigenspace for -4 is all the multiple of 6, -5. This, if you write as span, this also includes 0. This is actually a vector space because we know span is a vector space. Span of any vectors is a vector space. So this is called the eigenspace. So the terminology, this is called the eigenspace, right? So the eigenspace corresponds to lambda equals to -4. And this is the eigenspace, corresponds to lambda equals to 7. Okay, so these are just terminology. Again, more terminology. We need all this terminology because we want to be able to characterize when a matrix is diagonalizable, and we need all this terminology. And you will look at it. This is pretty straightforward. So just remember, these are just terminology, and we're going to use it later. Okay, so now we want to define something called the geometric multiplicity of an eigenvalue and the algebraic multiplicity of an eigenvalue. So the definition is this. So if lambda naught is an eigenvalue, it's the dimension of the eigenspace. So eigenspace is a vector space, so it has dimension. So the dimension of the eigenspace is called geometric multiplicity. So geometric, the word geometry, all right? Geometric is something that is a little bit harder, and it is actually the dimensions of the eigenspace of that eigenvalue. Algebraic multiplicity is the number of times that this particular factor appear in the characteristic polynomial. So when you compute the determinant, you will have things that's like this. equal to 0. So the number of times this eigenvalue appear in the characteristic polynomial is called the algebraic multiplicity. So algebraic multiplicity is about polynomial. Okay, so for example, this is matrix A. And if you want to find the eigenvalues, you will have to compute the determinant of A minus lambda I and set it equal to 0. So if you do that, this is what you get. And as I said, if you actually expanded it out, it will be a polynomial of degree 3, and which can be factored into this. So you can see you have a characteristic polynomial that looks like this. So immediately we know lambda equal to 2. This is eigenvalue with algebraic multiplicity 1. So algebraic multiplicity 1, because as a factor in the characteristic polynomial, this lambda equal to 2 appear only one time. This lambda equals to -1 is also an eigenvalue, but it will be something that we say that have algebraic multiplicity 2. It has algebraic multiplicity 2 because it appears twice. This eigenvalue appear twice as in the characteristic polynomial. So in the characteristic polynomial, you have it to the power of 2. So that's algebraic multiplicity. So pretty straightforward. The geometry, right? The geometric multiplicity is going to be a little bit more complicated. You actually have to solve for the eigenvectors. So you try to find the eigenvectors corresponds to lambda equals to -1. So put lambda equal to -1 into this determinant, and it will turns out to be put this lambda equals to -1 into this system, A minus lambda I, x equals to 0. Try to solve for x. So solve for x, where lambda now is -1. So put lambda equals to -1 to here, which means put all the lambda as -1. So you have this, row reduced to this. So you can see solving it leads to answer that looks like that. So you can see the eigenspace is spanned by these two vectors. So the eigenspace is spanned by these two vectors. The eigenspace for lambda equal to -1 is spanned by these two vectors. So by definition, this is a vector space that has dimension 2. Right, the bases, these are the bases. This can be taken as a basis for that space. They span the space, obviously, by definition, and they are linearly independent. You can check that. You can check that they're linearly independent. So this can be taken as a basis for that vector space. So the dimension is 2 because there are 2 vectors in it. So we call this geometric multiplicity. So we say the geometric multiplicity for lambda equals to -1 is 2. So the algebraic multiplicity is 2. Geometric multiplicity for this eigenvalue is also 2. All right, so in this case, your algebraic multiplicity for lambda equal to -1 is 2. Is also equals to the geometric multiplicity for lambda equals to -1. Okay, so we have another eigenvalue, lambda equal to 2. This is the one that appear one time. Okay, so you have algebraic multiplicity equals to 1. Right, algebraic multiplicity is equals to 1, and let's compute the geometric multiplicity. So we have to solve for x. So solve for x in this equations. Okay, so put lambda equals to 2. Okay, put lambda equal to 2 and solve for x, and you'll see that your x is in this form, which means that it is spanned by 1, 1, 1. So the eigenspace for this is spanned by the vectors 1, 1, and 1. So this obviously is a vector space of dimension 1. So the geometric multiplicity is known as 1 by definitions. Okay, so here we have, let's summarize. So here we have a situation where the algebraic multiplicity of lambda equals to -1, right? Lambda equals to -1 right here. Lambda equal to -1. We have algebraic multiplicity lambda. Okay, lambda equals to -1 have algebraic multiplicity 2, which is also equals to the geometric multiplicity. Lambda equals to 2 has algebraic multiplicity 1, and is also equals to the geometric multiplicity. And actually, let me tell you the punchline. There's a theorem which says that the geometric multiplicity, geometric multiplicity is always less than or equals to the algebraic multiplicity. So the geometric multiplicity can be less than or equals to the algebraic multiplicity. This is going to be the main problem that is going to cause us a lot of trouble, is because geometric multiplicity is less than or equal to the algebraic multiplicity. Because of that, we will have some problem in the second video. You do not know what's going on yet, but just try to introduce the terminology and the observations that in this case they are equal. But in general, geometric multiplicity can be less than the algebraic multiplicity, and this is going to be shown here in this example. So if you are asked to find the characteristic equations, means that we have to solve for the determinant of a minus lambda I, set it equal to 0. And if you do that, you will get this. Okay, which means lambda equal to 2. This eigenvalue has algebraic multiplicity 3, right? Okay, lambda equals to 4 has algebraic multiplicity 1, okay, because this is power 1. So if we compute for lambda equal to 2, we compute the eigenvectors. So we want to find the eigenvectors. We want to find the eigenspace actually. So we want to find the eigenspace for lambda equal to 2. We want to find the eigenspace for lambda equal to 4. So you compute this and you realize that the eigenspace for lambda equal to 2 is just span of this one vectors. So the basis for this eigenspace is just this. This is it span the eigenspace, and obviously it's a non-zero vector, so by itself, so it's independent. So the geometric multiplicity is actually 1. So now you can see that. Okay, so now you can see that for lambda equal to 2, so for lambda equal to 2, the algebraic multiplicity is 2. Actually, it's 4, right? It's 3. Let's see. It's 3. So the algebraic multiplicity is 3, but the geometric multiplicity is 1. So you can see that geometric multiplicity sometimes does not have to match the algebraic multiplicity. It can be less than it. And if you do the same for lambda equal to 4, we know lambda equal to 4 has algebraic multiplicity 1. And if you solve for the, look for the eigenspace, you will see that geometric multiplicity is also 1. So this one matches. Algebraic multiplicity and geometric multiplicity, they matches. But for the previous one, the lambda equals to 2, right? Lambda equal to 2, your algebraic multiplicity is actually 3, but geometric multiplicity is only 1. So again, this shows that geometric multiplicity can be actually less than or equal to the algebraic multiplicity. So right now you don't really know why is this important. This is just like some terminology, but it is critical in the second part of the video when we talk about diagonalizations. So right now, this entire video is just basically telling you what is eigenvalue, what are the eigenvectors, and what is the eigenspace, and what is the dimensions of the eigenspace, which is called the geometric multiplicity, and the number of times the eigenvalue appear as a factor, lambda equals to lambda naught, in the characteristic polynomial that is known as algebraic multiplicity. And key observation is that geometric multiplicity can be less than or equal to the geometric multiplicity. And that's that. That's the end of this video. And this is like the key things to remember before we move to the next sections. All right. Thank you very much.